impact.
Can you hear me?
Yeah, you're a little faint. Maybe speak up.
Can you hear me now?
Yeah, that's better.
Yeah. So up till now in this workshop, we have focused on the speciation and the abundance of carbon in different reservoirs in the inner and outer solar system. But I'm going to primarily focus on the origin of carbon back home on Earth. So basically, the topic of my talk is basically based on the delivery of carbon, nitrogen, and sulfur to the Earth. How were they delivered to the Earth at an early stage? So basically, what I'm going to do is I'm going to look at the carbon abundance in the bulk silicate Earth reservoirs and use them to find out what can they tell us about the origin of carbon on our planet. So over here in this cartoon, I have basically divided Earth into three primary reservoirs. There's an exosphere, which is primarily composed of the atmosphere, hydrosphere, and the crustal reservoirs. And then there's the mantle, and then we have the core. So carbon is present in all three of these reservoirs. In the exosphere and the mantle, carbon is present in the form of carbon dioxide or carbonates or graphite or diamond, while in the core, carbon could be possibly present in the form of iron carbides. So over short time scales of thousands or millions of years, carbon cycle in carbon exchange between the exosphere reservoirs controls the long-term climate and the habitability of our planet. But over longer time scales of billions of years, there's a carbon exchange that takes place between the mantle and the exosphere and has a primary control on the long-term habitability of our planet. So due to this exchange between the mantle and the exosphere reservoirs, I've clubbed both of these reservoirs together, known as the bulk silicate Earth. So what I'm going to do is look at the abundance of carbon in the bulk silicate Earth and see how it was formed. So basically, carbon content in the exosphere reservoirs is pretty well known, but the mantle carbon content is kind of poorly known. So we know the measurement of carbon in the mantle from the measurement of carbon dioxide and similarly incompatible elements like the CO2 by niobium or CO2 by barium ratios from minimally decayed basalts from the OIB sources and the MOB sources. So the OIB sources actually tap the lower part of the mantle, while the MOB sources tap the upper part of the mantle. And if the mantle is heterogeneous, then both of these sources could have different amount of carbon, and the net amount of carbon in the bulk mantle would actually be dependent upon the proportion of these sources in the whole mantle reservoir. Taking into account all these complexities, people have come up to a number that the carbon content in the bulk silicate Earth reservoirs is approximately equal to 80 ppm. But to develop a holistic picture of the origin of carbon, we need to hinge the carbon abundance in the bulk silicate Earth reservoirs with other volatile elements like nitrogen and sulfur. So basically over here I presented the bulk silicate Earth abundances of different volatile elements. The bulk silicate Earth abundance of sulfur is 225 ppm, carbon is 80 ppm, and nitrogen is 2.5 ppm. Over here I've plotted the carbon, nitrogen, sulfur abundances in the bulk silicate Earth normalized to carbonaceous chondrites. So basically this represents the carbon, nitrogen, sulfur abundances in the bulk silicate Earth and is normalized to carbonaceous chondrites, the CI chondrites. So if you look at this picture clearly, nitrogen is depleted in the bulk silicate Earth normalized to carbonaceous chondrites with respect to carbon and sulfur. And the carbon by sulfur ratio on the bulk silicate Earth is 0.5, and the carbon by nitrogen ratio in the bulk silicate Earth is pretty high, which is 40. So it is interesting to look at this number. So if you look at this, the carbon by nitrogen and the carbon by sulfur ratios, so the carbon by nitrogen ratio of the bulk silicate Earth is over here. And that carbon by nitrogen ratio is actually greater than all the carbon by nitrogen ratio of all the building blocks. And over here I plotted all the different chondrites that exist, that we have data for the carbon by nitrogen ratio, and the carbon by nitrogen ratio in the bulk silicate is a clear outlier. While if we look at the carbon by sulfur ratios in the bulk silicate Earth, the carbon by the sulfur ratio of the bulk silicate Earth is approximately, within error, is approximately equal to carbonaceous chondritic value. So the important thing to note over here is the carbon by nitrogen ratio in the bulk silicate earth is superchondritic, while the carbon by sulfur ratio in the bulk silicate earth is chondritic. So to look at what are the building blocks for these particular volatile elements, if you look at the delta 13C values over here and the delta 13C values and the delta D values over here. So the earth has delta 13C and delta T values that are completely different from the protosolar nebula. But these values cannot, but the delta 13C and the delta T cannot differentiate whether these volatile elements were delivered by comets or carbonaceous chondrites. But if you look at the delta 13C, delta 15N value and the delta 15N and the delta D plot over here, the Earth plots over here, while the protosolar nebula plots over here, and the comets plot over here. And it clearly shows that, especially for nitrogen and hydrogen, all nitrogen and hydrogen were basically delivered by carbonaceous chondrites rather than from comets or protosolar nebula. So chondrites, so it can be safely assumed after looking at this plot that carbonaceous chondrites, primarily CI chondrites, were the source of carbon, nitrogen, and hydrogen, and possibly other volatile elements in the Earth. So the key questions over here are, if we assume that carbonaceous chondrites were the source of all these volatile elements on Earth, when were these volatile elements delivered? Were they delivered during the formation of our planet, that is during core formation, or were they delivered post-core formation as a late veneer? And what was the delivering mechanism of these volatile elements? Were they delivered by smaller undifferentiated bodies like chondrites, or were they delivered by large and differentiated bodies? So if we assume that these volatile elements were delivered post-core formation via late veneer, via smaller undifferentiated bodies, then we can satisfy the carbon abundance in the bulk silicate earth as well as the sulfur abundance in the bulk silicate earth, but we cannot satisfy the nitrogen abundance in the bulk silicate earth. And if you look at the numbers over here, the carbon by sulfur ratio can be satisfied, while carbon by nitrogen ratio cannot be satisfied if we deliver the volatile elements to the earth via undifferentiated chondrites. So then you have to differentiate nitrogen with respect to carbon somehow. Either you have to lose nitrogen to an early atmosphere and that atmosphere was basically lost, or you have to lose nitrogen preferentially to carbon into the core of the earth. So to understand these processes, we need to look at planetary differentiation. So basically what you have is you have delivery of undifferentiated chondrites, and during those early stages of the earth, there could be a magma ocean that could be present under those set of conditions. After the delivery of undifferentiated bodies, we could have separation of the metal phase and the silicate phase. And when the metal phase and the silicate phase begin to separate out, then the metal phase ponds over the solid the metal phase ponds over the solid mantle over here, and the metal and the silicate phase and all the elements that are present in the magma ocean in the molten mantle over here, they can start to equilibrate with the metal phase as well as the silicate phase. If an element has a preference for the metal phase, then it wants to go, then it will preferentially go into the metal phase, and that metal phase would finally segregate and form the core. So basically, the idea is, so the carbon, nitrogen, sulfur abundances in the bulk silicate earth could have been set up by whatever was left post-core formation in the bulk silicate earth reservoirs. So to look at how these elements fractionate during the core mantle fractionation, people look at a parameter known as the alloy silicate, which represents the concentration of element divided by the concentration in silicate. This parameter is calculated from experimental studies. If this D value is greater than 1, then that element is a pseudophile element, that element wants to fractionate into the core. And if the D value is less than 1, that element is a lithophile element, it wants to stay preferentially in the mantle. So all these previous experimental studies have shown that the partition coefficient of carbon is much greater than that of nitrogen. If that is so, then carbon should have been a much more pseudophile element than nitrogen, and the carbon by nitrogen ratio in the bulk silicate earth, if all these volatile elements participated in core formation, then the carbon by nitrogen ratio in the bulk silicate earth should have been subchondritic, but actually that ratio is superchondritic. So this plot clearly shows that. So if these volatile elements were delivered by undifferentiated bodies during core formation, then the carbon by sulfur ratio in the Earth would have been subchondritic, and the carbon by nitrogen ratio would have been subchondritic as well. So volatile element delivery via undifferentiated chondrites, either during pore formation or post-pore formation as a late veneer, cannot satisfy the carbon, nitrogen, sulfur abundances simultaneously in the bulk silicate Earth. So to look at this, so people now generally assume that smaller during the stage of the protoplanetary disk, planetary embryos were formed, and when the protoplanetary disk dissipated, the Earth grew by the accretion of larger planetary embryos. So we want to see whether the volatile elements could be delivered to the Earth by a larger differentiated body. So to look at that, we look at the planet numerical simulations for planetary formation. So the red colored symbol show over here is volatile free material, and the blue colored symbol show over here is volatile rich material. As we go close to the sun, we have volatile depleted material, and as we move away from the sun, we have volatile rich material. So 0 million years represents the formation age of the solar system, and all the bodies that were accreted in the inner solar system were initially accreted from volatile depleted material. Between 1 to 10 million years, there was a migration of these giant planets from their present-day orbits. So Jupiter and Saturn moved inward and outwards, which displaced a lot of material from the outer part of the solar system into the inner part of the solar system. So what could have happened is small planetary embryos that would have formed from the accretion of volatile depleted material and volatile rich material, and one of those planetary embryos might have accreted to the Earth to satisfy the present-day volatile budget of the Earth. So this is the scenario I want to test. So this is a cartoon representing that particular scenario. So you have already differentiated proto-Earth that is basically volatile depleted. So the volatiles are delivered to the Earth by a differentiated planetary embryo, which itself has a core and a mantle. And these scenarios have been discussed in past by all these previous papers. So they have shown that the abundances of various kinds of lithophile elements in the bulk silicate Earth can only be satisfied if these elements were delivered by a differentiated planetary embryo at a much later stage of accretion of Earth. So to test this scenario, we perform metal silicate partitioning experiments. So what we do is we take up a metal phase and a silicate phase, and we melt them together in graphite capsules. So as we perform these experiments in graphite capsules, a metal phase and as well as the silicate phase are carbon saturated. So this is the light symbols represent the metal phase and the dark symbols represent the silicate phase over here. So what we do is we measure the carbon, nitrogen, sulfur concentrations in the alloy phase. We measure the carbon, nitrogen, sulfur concentrations in the silicate phase, and then we can come up with that parameter we talked about earlier, that partition coefficient. So once we look at the carbon, so as our experiments were performed in graphite capsules, our alloy phase as well as our silicate phase were carbon saturated. So what we saw in our experiments is when we use variable amounts of sulfur in our experiments, that is that when the sulfur content in the alloy melt kept on increasing, the carbon solubility in the alloy melt keeps on decreasing, which shows that in sulfur-rich alloys, the carbon solubility in the metal is very low, while in sulfur-poor alloys, the carbon solubility in the metals is very high. If we look at I'm sorry, I think these symbols changed, but this represents the partition coefficient of nitrogen. This is the nitrogen concentration in the alloy divided by the nitrogen concentration in the silicate as a function of sulfur content in the alloy melt. So the partition coefficient of nitrogen in the alloy does not change as a function of sulfur concentration in the alloy melt. While if you look at the partition coefficient of carbon in the alloy and silicate phase, so the partition coefficient of carbon is 100 when an alloy is sulfur poor, which shows that carbon is very highly pseudophile under these set of conditions. However, when the sulfur content in the alloy keeps on increasing, that is when the sulfur content in the alloy becomes approximately 25%, then the partition coefficient of carbon drops by an order of 2, which means that carbon becomes less pseudophile by an order of 2 if a body had a sulfur-rich pore. So what we want to do is, so we have a volatile depleted proto-Earth. We want to test the scenarios of accretion of these differentiated bodies at a much later stage. So either So the two scenarios could be that the core of this body could have been sulfur poor. If the core of this body was sulfur poor, then the carbon solubility in the metal would have been very high. And the other scenario would have been the core of this body would have been sulfur rich. If the core of this body would have been sulfur rich, then the carbon solubility in the alloy would have been very low. Then carbon in the form of graphite or diamond would have been exolved as a phase into the magma ocean of that body, and you can artificially enrich carbon in the mantle of this body. This is similar to the uralite parent body that we talked about yesterday. So to test these scenarios, what we want to do is we want to find out the composition of this particular impactor, and we want to find out the mass of this particular impactor. And we do a set of inverse Monte Carlo simulations. The unknowns the numbers that we want to fit in our inverse Monte Carlo simulations are the carbon, nitrogen, sulfur abundance in the bulk silicate earth, as well as the carbon by nitrogen and the carbon by sulfur ratios. And our variables are our thermodynamic relationships from our experimental data. We varied bulk sulfur, bulk carbon, and bulk nitrogen content in that impactor based on the chondritic values. So what we find in our simulations is, so this represents the bulk sulfur content, and this represents the sulfur content of the core. So all our simulations predict that the core of the impactor should have been sulfur rich. So if the core of the impactor was sulfur rich, then the carbon solubility under those set of conditions would have been very low. If the carbon solubility under those set of conditions would have been very low, then carbon would have been exolved in the mantle of that impactor in the form of graphite or diamonds. So the impactor could have been more like a uralite parent body. So these over here, we are trying to predict the bulk composition of the impactor. All our simulations predict that the bulk composition, the bulk carbon content in our impactor lies between 0.1 weight% to 0.5 weight%. So what our simulations actually predict is that the impactor need not be made completely of carbonaceous chondritic material. The impactor could have been made up of 10% of carbonaceous chondritic material, while other 90% would have been made up of volatile depleted material like ansatite chondritic material in the inner solar system. So our impactor could have been a heterogeneously accreted impactor. And then we wanted to find out predict the mass of the impactor, and all our simulations predicted that the mass of the impactor lies close to the size of the mass. So what we're trying to say over here is that carbon, nitrogen, and sulfur could have been delivered to the Earth by a differentiated mass-sized body with a sulfur-rich core. And these are our conclusions. Thank you.
You have time for a couple questions?
I have a question, actually.
Question in the room?
Have you looked at scenarios? So one of the things that might break some of the uniqueness in trying to back out the composition of the impactor is the fact that you can have these giant impactors occur where you lose more of the mantle than you do of the core of the impactor. If you basically have a partial accretion scenario, yeah. You still considering that could have happened, can you still say with the certainty that you have what the composition of the impactor is?
So yeah, so I think we have looked at these kind of numbers. So I think so that's a pretty valid question. When we have looked at these kind of numbers, so the two problems could have been you could either lose the mantle of that body, or you could have, or you could emulsify, or some of the core that goes into the proto-earth could have also equilibrated. And we have tried to take these things into consideration as well. So basically, if you lose the some part of the silicate, part of the mantle during those collisions, you need a bigger chondrite, a bigger impactor to deliver these volatile elements. So, but those things we have tried to do some sensitivity analysis, trying to do those things into considerations, like the loss of the silicate part or the equilibration of the core into the mantle as well of the proto-earth.
Okay, yes, question from Simone. Is this delivery due to late accretion, or does it come with the primordial accretion of the Earth?
So what we do feel over here is, so I think when people look at lunar basalts, so people believe that lunar basalts have pretty high amount of water. So basically we believe that So people have talked about that the volatiles could actually have been delivered pre-moon forming impact. But what our simulations actually predict is these volatile elements were delivered during the main stage of accretion, most probably during the moon forming impact. So it's not like a late linear scenario that these volatile elements delivered post-core formation.
He says he got it.
Yeah.
Any other questions? The speaker?
Other discussion for
Yeah.
this?
Any other discussion for this session?